Very good. So let's talk about ODE. Our objective for now is just a review of second order differential equations and high order differential equations. So nth order differential equations. So what we learned so far? First of all, recall that in previous chapters, we start talking about first order differential equation. We said that, hey, if y is equal to f of x, an nth order differential equation is written this way. An x, the nth derivative of y, plus an minus 1x, the nth minus 1 derivative of y, plus the middle terms, and a 1x y prime plus a sub 0x y equals to g of x. Remember that we said that if g of x is equal to 0, then we are dealing with a homogeneous nth order linear differential equation. So g of x is 0, it is homogeneous. And if g of x is not 0, it is called non-homogeneous differential equation. Very good. So this is nth order. In previous chapters, we say that, hey, for a first order differential equation, we're going to check to see if the differential equation is separable. Is it, for example, linear? Is it exact? Then some format was substitution, Bernoulli, and so on. Based on the classification of first order differential equation, a1 x y prime plus a sub 0 x y equals to g of x, we applied different methods, and we learned that, hey, sometimes we can apply more than one method to solve the differential equation on the given interval. We also learned how to graph and visualize the differential equation using either slope fields, isocyclines, and we also talked about the discussion in our homework about autonomous differential equations and how do we use the phase line to analyze the behavior of the equilibrium or stationary or critical points on the phase line. Okay, so we're done with first order differential equations. Are we stopping? Of course not. We have to move on to the second order differential equations and eventually higher order differential equations. In the second order differential equation that we introduced in chapter 4, we said that, hey, we need some terminologies. Well, before talking about the terminologies for second order differential equation, we try to classify differential equations with given conditions as initial value problem and also boundary value problem. So for initial value problems, well, you only had one x to deal with. For example, you had a(n)x yn plus the middle terms a1x y prime plus a sub 0 x y equals to, well, here suppose you're dealing with a homogeneous differential equation and your y at x sub 0 is y sub 0. You have some constraints, some conditions. After solving the differential equation, you can plug in those given values and solve the differential equation for a particular differential equations. However, for boundary value problem, a(n)x y to the n dot 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 a1x y prime plus a sub 0 x y. We had more than one x values to deal with. For example, we had y at x sub 0 equals to y sub 0, y at x sub 1 equals to y1, and so on. Boundary value problem. Remember that we introduced a theorem that guarantees that our differential equation has a solution and that solution is unique. So recall that. Our theorem says if ANX, AN minus 1x, dot, 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 A1x, A sub 0x, and G of x are continuous on an interval. And with the condition that your leading coefficient is not 0, ANX is not 0, then we can find a unique solution for the differential equation. So it means that we're not wasting our time. If these conditions are met, we definitely can find a solution which is unique on that interval like I. We start talking about linear operators. You recall that a linear operator is a function that transforms other functions. A linear operator is a function, let us call it L, that transforms in ordinary differential equation word, transforms other functions. In linear algebra word, transform vectors, transforms functions. And we say that, hey, a linear operator preserves linearity. A linear operator, the terminology that you're using, preserves linearity. What's the meaning of that? Preserves linearity. It means that if you have the sum of two functions, f plus g, it gives you the transformation of f plus the transformation of g. It also preserves the scalar multiplication. A linear operator also preserves scalar multiplication. What's the meaning of that? It means that if you have a scalar like C, L of CF can be written as C, the transformation of F, C is a constant. The scalar. Scalar, or another name, just a constant, just a number, value. Remember that we say that, hey, we have differential as linear operator. One example is L to be equals to the differential with respect to x or any independent variable that you have, which is called differential operator. also introduced the nth order polynomial operator. an dn an minus 1 dn minus 1 plus a1d. Okay, let me just add x plus a sub 0 x. Nth order polynomial operator. Very well. Another note for us. We know that d is the differential with respect to x. So dy is the differential of y with respect to x. Remember that d of d is d to the second. So if you want to write d of y, it becomes d dx d dx of y, which is the second order of y with respect to x. Then we generalize the idea that if you repeat this n times, this becomes the nth order derivative of y with respect to x. Let's go over one example. So your example on page 4 says any linear differential equation, any linear differential equation can be expressed in terms of d. Can be expressed in terms of d. For example, if you have the differential equation as the second derivative of y plus 5 times the first derivative of y plus 6 times y equals to 5x minus 3. Remember that we introduced the first derivative of y to be dy using the differential operator. The second derivative of y is d squared. So this guy is nothing but d squared, right? Plus, this guy can be written as 5 dy. And here you have plus 6 times y. On the right-hand side, we have 5x minus 3. Well, here if you factor out y, what's left is d squared plus 5d plus 6 equals to 5x minus 3. We're going to talk about this guy later. Let's just for now learn how to convert your differential equation using the differential operator. So guys, again, in the linear operators world, linear operators, Remember that a linear operator is a function. This is a function. In this world, you have some members. One of the members is d dx. L, which is represented as d dx, the differential with respect to x, is called the differential operator. It's denoted by d. D equals d over dx is called a differential operator. This is one example of a linear operator. So if you have, for example, a function, and you are taking the first derivative of that function, you represent that by f prime. If you're taking the second derivative of that function, it's represented by f second derivative, f double prime. And you continue this process. The third derivative, you put 3 of these. You get the third derivative of this function. But if I don't take any derivative, f to derivative 0, what's the meaning of that? It means that you get your function back. So your operator to 0 doesn't do anything. If you imply that to any function or any variable that is dependent on another variable, you get that variable back. Very good. Now we're going to talk about 2 functions, the linearly dependent, independent. New definition. And for those of you who have taken linear algebra or you're going to take linear algebra, this is the terminology that you're using. Definition of linearly dependent or linearly independent. So we say that 2 functions like f1 and f2 are linearly dependent if we can find constants like C1 and C2 which are not 0 at the same time, not all of them are zeros, such that if you form the linear combination of these 2 functions, that linear combination becomes 0. C1, F2 becomes 0. Okay. They are linearly dependent to each other. Okay. If not, then we say that they are linearly independent. Otherwise, we say F1 and F2 are linearly independent. So again, 2 functions like F1 and F2 are called linearly dependent if you can find non-zero constants like C1 and C2 such that the linear combination becomes 0. Otherwise, we have linearly independent functions. In linear algebra terminology, instead of working with functions, we usually introduce vectors in linear algebra. 2 vectors like u and v. are called linearly dependent, the same definition. If we can find, or if there exists C1 and C2, the constants which are not zero. Zero, such that C1 V plus C1, let's write down U plus C2 V equal to 0. In linear algebra, we work with vectors, but eventually we can form the space of all functions, and then we can discuss about subspace of those functions for solutions of differential equations. There are many overlaps between linear algebra topics and differential equations topics. And the same, if not otherwise, we call them linearly independent. Give us an example. Okay. Let us take a look at this example here. A very simple example. Let f1 be x squared and f2 be negative 2x squared. Are these two linearly dependent or independent? Very good. So what do you think, everyone? There you go. So can you find C1 and C2 such that if I multiply the first function by C1 and multiply the second function by C2, the outcome is equal to 0? Guys, take a look at this. If I just write these this way, if I just write down x squared minus 2x squared equal to, if I simplify this, I get negative x squared, which is not equal to 0. So if you just write it this way, so you say that, hey, they are linearly independent, but our goal is to try to see if we can find C1 and C2. So our goal is to try to find C1 and C2 somehow magically makes this linearly dependent. So our job is to find C1 and C2, not just add these together and say that since the sum is a function, negative x squared, a quadratic function, they are linearly independent. No, our goal is to try to find C1 and C2. We try to find C1 and C2. So, okay, if I multiply this guy by 2, C1 is 2 and C2 is just 1. Let's see what happens. I get 2x squared minus 2x squared, which is 0. I found C1 and C2? Yes. So it means that they are linearly dependent. F1 of x, which is x squared, and f2 of x, which is negative 2x squared, are dependent, linearly dependent. Okay, very good. Now I expect you to ask, it takes forever to find C1 and C2. This one was just a super simple example. I could just look at it by going back to even elementary algebra, find C1 and C2. What if we have more complicated functions? Do we have any trick? Luckily for us, somebody came up with a trick, a technique, Wronskian. So, again, Wronskian is used for the function, and then we need the derivatives of the functions as well. So the method to check if functions are linearly dependent, independent is Wronskian. Wronskian says, well, suppose you have functions f1, f2, f3, fn, and suppose you have the derivatives. You can take the derivatives of them, and n minus 1 derivatives of those n functions exist. Let f1, f2, and fn be functions such that they have n minus 1, at least n minus 1 derivatives. The Wronskian is defined as the determinant. So the Wronskian of f1, f2, comma, fn is equal to the determinant on the very first row. You're going to list all of these functions. f1, f2, dot, 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 fn. On the second row, you're going to find the first derivatives of these functions. f1 prime, f2 prime, dot, 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 fn prime, and you keep going. The second derivative, the third derivative, the fourth derivative, and you stop at f of n minus 1. The n minus 1 derivative of f1, the n minus 1 derivative of f2, and the n minus 1 derivative of fn. You find this determinant. If it's equal to 0, then you say that they are linearly dependent. 0, dependent. If the determinant is not 0, then they are independent. This trick, this method makes life much more easier. For example, for this guy, if you form the Wronskian of x squared and negative 2x squared, this becomes, well, x squared, you're going to copy down these functions here on top, then it's a 2 by 2 matrix, the determinant of a 2 by 2 matrix, you get 2x, and you get negative 4x. This becomes negative 4x cubed plus 4x cubed, which is equal to 0, so they are dependent. Wronskian is 0. So they are dependent. Okay, guys, keep that in mind that here we are introducing two linearly dependent functions. We applied two methods to show that, hey, they are dependent to each other. They found C1, C2, and we also used the Wronskian of these two functions. So here's an observation. The observation here says, well, I have linearly dependent functions, and if I divide these two, for example, x squared divided by negative 2x squared, the outcome is a constant. The outcome is a constant. So you should be asking, what if I have linearly independent functions? Is the outcome is going to be a constant, or is it a function? Let us go over one example together. Okay, let me write this example here. We already learned about the definition. So another example. R e to, let me follow the note, e to 3x and e to negative 3x linearly dependent, independent, so since I have a technique, Wronskian, I'm going to apply that method. Why not? The Wronskian of e to 3x e to negative 3x is equal to, well, I need a 2 by 2 matrix and find the determinant of that matrix. On the first row, I'm going to copy down the functions that I have. E to 3x, e to minus 3x. Well, on the second row, I'm going to take the derivative. The first derivative of e to 3x using, well, the methods that you learned in elementary calculus, it gives you 3e to 3x back. If I find the derivative of e to negative 3x, I get negative 3 e to negative 3x. Well, the determinant, first of all, you have to multiply these two, you get negative 3 e to 3x times e to negative 3x minus 3 e to 3x times e to negative 3x. So these two have the same base. Combine the exponents, you get negative 3 minus 3, which is negative 6, and it's not 0. Well, it's not 0. What's the meaning of that? It means that these functions are linearly independent from each other. So our conclusion, e to 3x and e to negative 3x are linearly independent. So just a quick observation. If I divide these two, what do I get? E to the x divided by e to negative 3x, I forgot to write down 3, which is equal to e to 3x times e to 3x, or e to 6x, which is not a 0, which is not a constant. Not a constant. So, guys, this is an important observation that we have. If you have linearly dependent functions, the division between them, the quotient between them, always results in a constant. But if they are linearly independent from each other, the outcome of their quotient or their division is not a constant. This is an important observation for us. Why is that? Because eventually we're going to introduce a method, the method of reduction of order. If we have one solution of the differential equation, we can find a second solution for that differential equation. So remember that if you have taken linear algebra, or if you would like to take the linear algebra, or if you have taken some machine learning courses, if you're familiar with this, in machine learning, our goal, our machine learning, deep learning, our goal, one of the goals is to do the classification. So when you're doing classification, one of the very famous methods is the method of PCA, principal component analysis. Well, there, for example, you have a bunch of points, and you want to apply PCA method. Some points are here, clustered around here. Some other points are clustered around here, for example. And this is the axis that you have for your classification. So what they usually do, they change these two axes to X and Y. Well, there they have to work with linearly independent vectors, find those linearly independent vectors and apply that method so they can change the axis. So another example for you. Here we have a differential equation, okay? I'm going to give you this differential equation. Consider the following differential equations. You have the third derivative of y minus 6, the second derivative of y plus 11y prime minus 6y equal to 0. Okay. So this is the third order differential equation. This is the order differential equation. I'm going to give you three functions. y1, e to the x. y2 is e to 2x. And I'm going to give you y sub 3, which is equal to e to 3x. E to 3x. The very first question that I have is, are these solutions for the differential equation? Okay. Are y1, y2, y3, this set, form a solution for the third order differential equation? And the second question that I'm having, are these functions linearly dependent or independent? Very well, let us check to see if each one of these is a solution for this differential equation or not. So first of all, to check to see if y1 is a solution, we need to find the second derivative, the first derivative, the third derivative, and plug this into the differential equation and check to see left-hand side and right-hand side are equal to each other or not. So y1 prime is e to the x. We all know that is equal to the second derivative, it's equal to the third derivative. We don't have any algebra to do. They are all equal to each other. You can continue taking the derivative of e to the x. So we get e to the x minus 6 e to the x plus 11 e to the x minus 6 e to the x. So, well, let's see. What do we have here? We have 12 e to the x minus 12 e to the x, which is 0. So far, so good. So e to the x is a solution for this differential equation. What about e to 2x? Well, we have to do a little bit of calculus, elementary calculus, nothing very hard. Y prime is 2 e to 2x. The second derivative is 4 e to 2x. And the third derivative is 8 e to 2x. Now we just plug that in. We have 8 e to 2x minus 6 times 4 e to 2x plus 11 times 2 e to 2x minus 6 e to 2x. Well, let's check to see. Here we get 8 e to 2x minus 24 e to 2x plus 22 e to 2x minus 6 e to 2x. Well, so here you have negative 8 plus 8, which is just 0. Left-hand side and right-hand side are equal to each other. So this guy is also a solution. E to 2x is a solution of the differential equation. And finally, e to 3x. For e to 3x, the first derivative is 3 e to 3x. The second derivative is 9 e to 3x. And the third derivative is 27 e to 3x. So let's just plug that in. Here we have 27 e to 3x minus 6, 9 e to 3x plus 11, 3 e to 3x, and minus 6 e to 3x. So let's see, here you have 27 e to 3x. You can factor this out, 27. Which is 0. Very good. So as you can see, e to 3x is also a solution for the differential equation. So it means that this set, the set including e to the x, e to 2x, e to 3x, is a solution set for the differential equation. So we call this set a fundamental set. I'm learning something new. This set of the solutions is called the fundamental set if they are linearly independent as well. If they are linearly independent. Okay, so let's find the Wronskian. The Wronskian of e to the x, e to 2x, e to 3x is equal to, well, in the first row, we're going to copy down the functions. On the second row, the first derivative, e to the x, 2e to 2x, 3e to 3x, and on the last row, e to the x, 4e to 2x, and 9e to 3x, which is equal to, well, so we get e to the x times, here the multiplication gives you 18 e to 5x, and you get negative 12 e to 5x minus e to 2x, parentheses, well, here we have 9 e to 4x, minus, here we have 3 e to 4x, plus, finally, we have e to 3x times, very well, we get 4 e to 3x, minus 2e to 3x. So if we simplify this guy, we get 6e to 6x minus 6e to 6x plus, here you have 2e to 6x. These two are opposite of each other. You end up with 2e to 6x, which is not 0. So the Wronskian is not 0. It means that they are linearly independent from each other. So this set is called the fundamental set for the differential equation. So we're going to have a theorem. Let me erase this for you and write down the theorem. This theorem says let a(n)x, the n derivative of y, a(n minus 1 of x, the nth minus 1 derivative of y, plus the middle terms a1x, the first derivative, plus a sub 0x, y equal to 0. Suppose we have the nth order homogeneous differential equation. Let be an nth order homogeneous differential equation. Suppose you have the fundamental set. Let the set f1, f2 dot 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 Fn. Or you can write it as y1, y2, yn. It doesn't matter. Be a fundamental set. What's the meaning of that? It means that these are linearly independent, so the Wronskian of F1, F2, and Fn is not 0, and each one of these is a solution for this differential equation. And each f sub I between 1 to n, is a solution for the differential equation. Then the general solution of the differential equation can be written this way. Y is equal to C1 F1 plus C2 F2 plus Cn Fn. Ci's, I is bounded between 1 and n, are constants. Don't forget your interval as well. On the interval, there you go. So suppose you have this case. You have a differential equation and nth order linear homogeneous differential equation. Now we're going to make it non-homogeneous. Non-homogeneous. Suppose you have the fundamental set. It means that you have a solution set that, okay, that satisfies the homogeneous differential equation. For ANX yn plus dot 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 a1x y prime plus a0x y equal to 0. Suppose you have your fundamental set for the homogeneous portion of this differential equation. Let f sub p, or let's just convert them into y1, y2, yn. Again, this is just a representation. Y2, yn, yi. Let y sub p be a particular solution of the differential equation, non-homogeneous differential equation of non-homogeneous differential equation. In this case, the general solution is y equals to C1 y1, C2 y2, Cn yn plus your particular solution y sub p on the interval y. C1, C2, Cn are just constants. So in general, if you have a non-homogeneous differential equation, first you write it in the form of a homogeneous differential equation. You're finding the fundamental set for that differential equation. Then if you have some initial values, if you have initial value problem, you're going to find the particular solution as well. It might be more than one particular solution. So you might have more particular solutions. You're going to add those to the rest of the general solution that you found using the fundamental set. Very good. So let's go over one example to feel more comfortable about this theorem. I'm going to go back to my previous differential equation, which was homogeneous, and make it non-homogeneous. Take a look at this example. Consider this differential equation. The third derivative of y minus 6, the second derivative of y, plus 11y prime minus 6y equals to 3x. Okay, very good. In previous example, note that in previous example, for the homogeneous part, of the differential equation, we have the following. The third derivative of y minus 6, the second derivative of y, plus 11y prime minus 6y equal to 0. We found 3 solutions. Guys, please pay attention. You have the third order differential equation. This is the third order linear differential equation with fundamental set e to the x, e to 2x, and e to 3x. All right. For the homogeneous part, we have 3 solutions: y1, y2, y3. Now, if you just consider the non-homogeneous part, if you plug those in, they don't satisfy this non-homogeneous differential equation. I'm going to give you a particular solution for this differential equation. For this non-homogeneous differential equation, consider the given. So I'm giving you, I haven't taught you how to find it yet. I'm just giving you the particular solution. Consider the given particular solution y sub p equals to negative 11 over 12 minus a half x. This is a particular solution because it doesn't have any parameter. You don't have any C1, you don't have any C2, you don't have any C3, you don't have any parameter. I'm giving you a particular solution. Now I ask you, what is the general solution for this differential equation? You have your fundamental set for the homogeneous part. You have a particular solution for the non-homogeneous part. So, in general, the solution is y equals to. We start by taking the fundamental set elements. C1, y1, C2, y2, C3, y3, plus your particular solution. Particular solution. But what is y1? What is y2? What is y3? What is y sub p? The general solution is y equals to C1 e to the x plus c2 e to 2x plus c3 e to 3x plus your particular solution, which is negative 11 half over 12 minus a half x. So this is the general solution for this third order differential equation. Our final answer. We divide up the differential equation into homogeneous part to find a fundamental set. After finding the fundamental set, you might have particular solution or more than one particular solutions. That depends on how the initial values are defined. So the general solution for this non-homogeneous differential equation must be written as a combination of elements in your fundamental set plus your particular solution. This is always true.